Hey guys, welcome back. This is our final lesson in chemistry on the acid-base unit. So we're looking today at hydrolysis. So basically what this means, well, let's bring it back a little bit. When a neutralization reaction occurs, you get water plus a salt, right? That's, grade 9 science here. However, we're going to look at this a little differently. Sometimes an ion from the salt could react with the water itself, causing a shift in pH. That process is called hydrolysis. And so to figure out if your pH is going to shift because of the salt you've formed, you have to figure out how likely your ions are to combine with either water itself or more likely some of the ions produced by water's ionization, autoionization. So water breaks 1 times 10 to the negative 14, right? Gives you some hydronium, some hydroxide. Some of it breaks down. And so some of the ions from your salt might react and pull the hydronium out, or might react and pull the hydroxide out. And if that happens, it's going to shift your pH on you. Now, the easiest way to kind of walk through this is really to look at some examples, and you'll see what I mean. So we're going to add potassium iodide to water. So just Ki. No H's, no OH's, just Ki, the salt, right? Is the resulting solution going to be acidic, basic, or neutral? So what you have to do is look at both ions that Ki would form. So here's ion number 1, just the iodide ion, right? You got I minus. So when I put Ki in water, I can either get K plus or I can get I minus. I'm going to look at them both. But let's start with I minus. Doesn't really matter which one you start with. Now, this ion is negatively charged, which means it's going to attract something positive, which in our case is not hydrogen. Oops. Hydronium. So if I put I minus in water, it's going to attract, the hydrogen off of water, and you're going to get Hi and OH minus. So if I were to put iodine in water, the only thing it can do is pull hydrogens to itself, and I'd be left with Hi and hydroxide, which means I should be left with a basic solution. But this is an equilibrium, right? It goes both ways. So you got to figure out, is it going to be mostly on this side, in which case it'll stay neutral, or is it going to be mostly on this side, in which case it'll be basic? So how do you figure out which way it's going to go? Well, what you're going to do is you're going to look at this right here. You've formed hydrogen iodide. So I minus, its conjugate acid, is Hi. And if you look at your acid-base chart, hydroiodic acid is a very strong acid, which means it completely dissociates. If it completely dissociates, it's going to be forcing the reaction in that direction. That's some Le Chatelier's principle stuff. So the more Hi is going to completely dissociate, it's going to push itself back towards the I minus side, which means the reverse direction is strongly favored. I'm not actually going to make almost anything here. Whenever I make Hi, it's going to fall apart right away. It's a strong acid. I'm going to have almost nothing there. So it's not going to favor the OH minus, so I'm not making any hydroxide. So I should not end up with a basic solution. So now my options are, it could be acidic or it could be neutral. Another way to look at this is Hi is a strong acid, which means its conjugate base, what I started with, is a very, very weak base and unlikely to steal a proton or to pull hydrogen out. All right, so we've determined not basic, and we've looked at iodide. Let's look at the potassium side of things. Potassium, being positive, would look to combine with hydroxide. Now, where do we get hydroxide? From the dissociation of water. So that's this right here. I got 2 H2Os, and it's just going to give me 1 hydronium and 1 hydroxide, right? And the potassium is going to come along. So this is like step 1, step 2. It's like a reaction mechanism almost. The potassium comes along, and it's going to grab the hydroxide to form KOH. So what is our net equation? Well, I have OH on this side and OH on this side. So my net equation is K plus 2 H2Os gives me KOH plus hydronium. So again, the potassium ion is going to form acid in the solution. But same question as last time, which way does this equilibrium push? If the equilibrium is pushing towards the reactants, well, then I'm not going to get any hydronium, and it'll be neutral. If the reactant is pushing towards products, if it's pushing this way, then I'll get a bunch of hydronium, then I will have an acidic solution. So, same plan as before, you look at the conjugate base. KOH is a very strong base. There's not a lot of them, right? Sodium hydroxide, potassium hydroxide, those are the strong bases. There's a couple other ones in there, but KOH should be something you recognize right away. That's a strong base. It's dissociating 100%. Whenever I form this KOH, it's falling apart again right away, which means I'm going to be heavily favoring the left side of this equation, the reactants. So that reverse reaction is favored, which means I'm not making any hydronium. Anytime I make KOH and hydronium, they're going to recombine and go back the other way. So the net effect of both ions, I'm not making base, I'm not making acid, no hydronium, no hydroxide. This salt has no effect on pH, which means this would be a neutral solution. So Ki would give you a neutral solution. Now let's look at an example of one that isn't. We add NH4Cl to water. Let me rewrite that so it's got a subscript. That's better. Is the resulting solution acidic, basic, neutral? All right, start with our chlorine ion. Chloride, being negative, is going to pull the hydrogen to itself, and so you end up with HCl and hydroxide. Now you guys know hydrochloric acid, very strong acid. It's going to fall apart right away, which means we are definitely pushing the reaction back to the left. So we're just going to have water and chloride. Those are both neutral. Oh. So chloride staying in ionic form. We're not making any hydroxide, so we're not making a basic solution. Let's check the other side. Ammonium, being positive, it's going to want to react with the hydroxide. So we start by writing out the dissociation of water. Then we write out how does the positive one react with the hydroxide. So in this case, it makes ammonium hydroxide right here. Then you write your net equation. My hydroxides cancel. I've got ammonium plus a couple of waters gives me ammonium hydroxide plus H3O plus. And so again, I got to figure out ammonium hydroxide, strong base or weak base? Well, I mean, there's not a lot of strong bases out there, right? And ammonium hydroxide, you've probably never even heard of, which is a good sign that's not a strong base. If it's not a strong base, which it isn't, it is a weak base, it's not dissociating very much, which means as we form it, I remember when we make the NH4OH, we also make hydronium, right? They come together. They're a package deal. So because it's a weak base, it's not going to dissociate much. It's going to stay in solution, which means these are going to shift that away. So it's not going to dissociate. It's not going to push the equilibrium back to NH4+, which means we're going to get some hydronium floating around. This is actually going to be in solution. So instead of being neutral, I'm going to have a little extra hydronium. And so this salt actually makes the solution acidic. So if I were to put NH4Cl in water, I'd end up very slightly acidic. One more example here, because it takes a little bit to wrap your head around the process. Sodium nitrite. Yeah, NO2 is nitrate. Sodium nitrate, add that to water. Let's look at sodium first. Sodium, it's a positive ion, right? So it's going to attract the negatives, the hydroxides. So I write out the dissociation of water. I write out how sodium combines with hydroxide. And dissociation of water is always the exact same, right? It's 2 waters gives you OH and H3O+. So net equation, I've got my sodium plus 2 waters are going to give me, so my hydroxides cancel, sodium hydroxide and hydronium. Now, which side should we shift towards? Well, look at your conjugate base. Sodium hydroxide. Is that conjugate base strong or weak? Man, sodium hydroxide. It is the go-to strong base. This one is for sure going to be dissociating completely. And when it breaks down completely and dissociates, it pushes the equilibrium the other way, pushing it away from H3O+. So, no H3O+ created. We're staying neutral. What else do I got? I got nitrite. All right, so nitrite plus water. It's going to take a hydrogen, and I end up with HNO2 and OH-. Nitrous acid. Now, be very careful. HNO3 is nitric acid, very strong acid. HNO2, though, not so much. If you take a look at your acid base list there, you can look up nitrous acid, and it's about halfway down. It's got a Ka of 5.1 times 10 to the negative 4. That is less than 1. That is a small number, which means this is a weak acid. Weak acid means what? Weak acid means not dissociating. If it's not dissociating, what does that mean? Well, that means our equilibrium shifts towards it. It's going to shift to products. If it's not going to break down, we're going to be trying to make it. So our entire equilibrium is going to go this way, which means what am I making? I'm making nitrous acid, and I'm making raw hydroxide. So even though I'm making nitrous acid, you'll be like, oh, I'm putting acid in there, right? This acid isn't dissociating. It's not giving us H3O+. It's not contributing to pH. As I'm creating this, I'm creating hydroxide, and hydroxide definitely contributes to the pH of a solution, right? And so as we shift the products here, we create OH-. So when looking to see whether something's acidic or basic, you're not looking to see if there is an acid present, because this is an acid. You're looking to see if there's hydronium or hydroxide. So because we've created hydroxide ions, and on the other side, we didn't create anything, the solution will be basic, because we've got hydroxide ions floating around. Now, that's the thinking that goes into all this. There is a bit of a cheat sheet to maybe help you out a little bit. If your cation comes from a strong acid, and your anion comes from a strong base. So strong acid means total dissociation. Anion, strong base, total dissociation, means your pH is going to sit around 7, right? So if I had like a sodium ion, that'll give me sodium hydroxide. The sodium ion came from a strong base. And if I had, here, let's look, NaCl. Where would these come from, right? Na would come from NaOH, because it's positive. Cl would come from HCl. That's strong, that's strong. Result is pH 7. Because they're both strong, they completely dissociate. They're not giving you any hydrogen or hydronium in the solution. And kind of vice versa, right? If one is from a weak acid or from a weak base, that's going to shift your pH. So if your anion came from a weak acid, let me just find a weak acid on this list here, and one that's easy to write. Hydrogen selenide. Cool. Okay, so let's say I had Na2Se. Okay, I'm going to put this weird salt into water. Well, the sodium comes from, sodium being positive, has to match with something negative, the hydroxide. And the selenide, being negative, has to match with something positive. So I'd have H2. So this is strong base. This is weak acid, right? And so if we've got a weak acid, that's going to shift our pH, because one is weak and strong. So what would actually end up happening here? H2O plus Se minus would give me H2Se plus OH. I'd end up with a basic solution. So if your acid, if the conjugate acid is weak, then the solution is a base. If the conjugate base is weak, then if conjugate base is weak, then your solution will be acidic. The only time it gets real tricky is if both come from weak acids and weak bases. Then you've got to actually take your chart out and look at Ka and Kb and figure out, okay, what is stronger, the acid or the base? And that'll tell you, like, if the acid is stronger, it has a weaker conjugate base. So if the conjugate base is weaker, the whole thing should end up being slightly acidic. So it takes a little bit to wrap your head around. There's going to be a worksheet posted for this, so you can kind of play around with it and see if you can make sense of it. The answer key will have whether it's acidic or basic, but it's not actually going to include the reasoning for it. So that's going to be kind of the tricky part of that one. You'll have to prove your reasoning. So thanks for watching, guys, and that's going to wrap up our chemistry unit.